Hi everyone, it's almost noon. A perfect time to relax for a moment. For those of you watching this video, this time, we'll discuss something very interesting. This concept will later be used to generate electricity. We'll start with a circular conductor. Let's assume this conductor is in the YZ plane. On the left side, there's the north pole of the magnet. On the right side, there's the south pole of the magnet. Between these magnetic poles is a magnetic field. Its direction is from the north pole to the south pole. Since this magnetic field doesn't originate from the circular conductor, we can think of it as an external magnetic field. Some external magnetic field lines penetrate the surface of the circle. We'll only show the lines of force that penetrate the surface for ease of visualization. Now, the circular conductor is rotating counterclockwise. Notice how many of the magnetic field lines penetrating the surface of the circular conductor are changing. What does this mean? It means the magnetic flux through the circular conductor is changing. This change causes an induced EMF to be generated. Based on Lenz's law, an induced magnetic field will be formed. An induced magnetic field will increase the lines of force toward the positive x-axis. To produce this induced magnetic field, an induced electric current will flow in the conducting loop. Its direction is counterclockwise. The presence of an electric current necessarily creates a voltage difference. However, after the conducting wire passes through the XY plane, the induced current changes direction. This ensures that the induced magnetic field always points toward the positive x-axis. And so on. Let's discuss this using Faraday's law. First, let's write Faraday's equation for induction, epsilon equals minus n d phi dt. The magnetic flux itself is influenced by B, A, and the cosine of beta. The diagram above seems very complicated. Let's simplify it to something like this. We see that initially, vectors B and A are in the same direction, or beta is 0 degrees. Next, the conducting loop rotates counterclockwise. Beta begins to increase, and vectors B and A are no longer in a straight line. We see that the magnitude of vector B remains constant because it is an external factor. The magnitude of vector A also remains constant because the circle does not change in size. The area of the circle is constant. Therefore, the values of B and A can be excluded from the calculation of d dt. If we have studied rotational kinematics, this beta value corresponds to the angular displacement of the conducting loop. This angular displacement can be calculated using the equation beta equals omega t, where omega is the angular velocity of the conducting loop. Now, cosine is a function of time. We can perform the derivative of the cosine of omega t with respect to time. This value is minus omega sine omega t. Minus times minus is plus. This is the induced EMF voltage in the conducting loop, epsilon equals NAB omega sine omega t. The presence of the sign factor here causes the direction of the induced current to change direction periodically at certain intervals. This is consistent with the experimental data. Hopefully, this tutorial is helpful. And don't forget to watch the next video.
I am waiting.